So please welcome Trent. He is a principal software engineer at NVIDIA, and he is going to talk about parallel PyTorch with free-threading Python.
All right, thank you very much. Haven't rehearsed this. Apparently I have 35 minutes, so we'll see how that goes. So my name's Trent Nelson, principal software engineer at NVIDIA. Have always been very interested in Python and free threading, and today we're going to dig into some of the aspects of getting PyTorch model inference working in parallel contexts, as well as just some other cool things you can do now that free threading has been mainlined. So before we start, who knows what the global interpreter lock is? Okay, that looks like pretty much, I would say 80% of the people. Have you ever been annoyed by the global interpreter lock? Probably about 50% of people. And are you excited at all by Python free threading? Is this like a cool technology to you? All right, we've got some double hands, probably about 30% of people. And are you currently using Python free threading? Wah wah, 0 hands. All righty. Did you use GPUs at work? All right, we got about 10%, 15%. And then 3 answers, both AMD and NVIDIA? Mostly only NVIDIA? Okay. And then any AMD? Okay, no AMD, everything NVIDIA. I guess I've already covered some of this. So software engineer by trade, not a data scientist, not a quant, not a machine learning expert. Thankfully, I've worked side by side with many folks that do those trades, so I have an appreciation for that discipline of engineering. Prior to here, I was at Voltron, CrowdStrike. When CrowdStrike took out the world, I checked my notes. The crash wasn't to do with my code. I didn't work on that filter, so. But I did work specifically on that part of the Windows kernel module, but that was a very amusing thing to wake up to. Tezza and Continuum. Now Anaconda. So this talk is inspired by an article that I wrote earlier this year. Prior to joining NVIDIA, I worked with OpenTeams and Quansight for about 3 or 4 months, and Meta indirectly essentially sponsored me to work on an article about PyTorch and how it worked with Python free threading. So if you go to trent.me/articles, it's the first one there, the PyTorch and Python free threading. It has a lot more details about anything that you find here today. So yeah, if any of this stuff tickles your fancy, you'll find a lot more information about it on the article there. So quick overview. What's Python free threading? We're going to cover just the general concept of it. A crash course on PyTorch and LM. By crash course, it's basically me informing you of what I did to try and bootstrap myself so I could train a GPT-2 locally. So there's just no way you could get into the details of a LLM in 10 minutes. We're going to cover this thing that I came up with called Parallelopedia, which is a multi-threaded pure Python async IO based HTTP server that leverages all of the bells and whistles that you get with Python free threading. We're going to take a quick look at the parallel PyTorch inference via a streaming async IO HTTP server. And then just for funsies, we'll also, in that same process, host all of Wikipedia. From 2015, the reason it was from 2015 is because I got a lot of this stuff working with PyParallel back in the day, and I didn't get time to do it on a new 2025 dump. So what is Python free threading? The global interpreter lock prevents 2 or more threads simultaneously running bytecode. Generally, programs are required to release the GIL when they do anything of interest or anything that's consuming CPU time, or any system calls, so like opening a file, socket transfers, that type of stuff. So you generally get this thing where Python is time slicing between all of the threads. So releasing the GIL allows another Python thread to acquire it. If no one's releasing it, then Python's just going to basically give you, I think it's like 50 or 80 bytecode executions before it will decide to switch to another one. So you kind of get this like round-robining-ish behavior. Not great, though. You're not going to be leveraging multiple cores in a particularly efficient way. So the story of the GIL. I stole this from my other colleague who did this slide in his presentation. I may as well just hijack it already. So there's been 2 attempts that I'm at least going to talk about here of trying to remove the GIL. It's interesting to note that pthreads came out in 1995. Python 1.5 had the threading module 3 years after the introduction of pthreads. Greg Stein in 1996, before who even had access to like multiprocessor machines there, he came up with a free-threaded patch that was very ambitious, and we'll cover that in a little bit in the next slide. The first multi-core, and again, I didn't fact-check this, and I hopefully my colleague that prepared this did fact-check this, but the first multi-core CPU didn't come available until 2001. Granted, we had like multiprocessor machines, so SMP machines, but the first multi-core wasn't a thing until 2001. And then a big lot of nothing. I took a crack at it in 2012, 2015 timeframe. And then finally, someone did it with engineering rigor, and we now have Python, initially released last year, the Python free-threaded build. So the first attempt, Greg Stein, based on Python 1.4. Also, I don't know if you can see it, there's a whole bunch of links down the bottom here. So this deck is available online, and I'll put some links up at the end. But if you're interested in more information about any of this, there's a whole bunch of links on the bottom there that are obviously unintelligible at this distance, but I will share the deck link at the end of this. The way Greg approached it was to introduce fine-grained locking everywhere, so just lock all of the things, destroyed existing single-threaded performance, anywhere up to like 40%, and it really didn't offer desirable multi-threaded gains to offset that single performance hit. So it never got mainlined into Python. And I mean, like 1996, like multi-processor systems were kind of expensive and out of the reach of certain, like even industry, let alone consumers. Still, Greg, great job, tackled a lot of important stuff, and a lot of stuff that he sort of pioneered persists to this day, such as like the separation of global state into per thread state. My attempt in 2012, it was based on Python 3.3-ish, removing the GIL without actually removing it. So basically, I didn't build in free threading. You don't create the threads. We create the threads for you behind the scenes, and we call these threads like parallel threads. And then the idea behind PyParallel was like, as long as we can come up with a quick way to detect if we're one of these parallel threads, then when we need to do something that's thread sensitive, as long as we can quickly detect, we're a normal GIL holding Python thread, then do what we normally do the normal incref. If we're a parallel thread, do something else. I realize the word else is doing a lot of heavy lifting in this sentence, but it was a whole bunch of things where I just instrumented the macros and then diverted to like a thread safe alternative. PyParallel website's there. Actually, you can still download it. I probably should take it down. It's not doing anyone any favors, but it was really fast at the things that it did well. So yeah, there's a website here. All these like, linear scaling. That's great. Nice little CDFs of the latency and it was actually like faster than a lot of like C-based Linux things. When, circa 2015 at least. There's also on speaker deck, there's I think it's like 156 slide that a lot of this deals with OS specific, the nitty gritty behind like asynchronous IO and parallel computation. So it's a pretty useful reference to this day. So pros and cons, I'm gonna skip through this. So successful proofs of concept, I'd show that you could at least do linear scaling, great performance, as long as you were writing like idempotent TCP socket servers. I kind of hacked in NumPy, DA-tree and PyODBC to support. All the async IO machinery, it was really fast. It was, just because of the way that I wrote like the async loop. The cons were long and distinguished, so you could only leverage multiple threads via an async socket server. There was no free thread support. There was a huge list of things you couldn't do in parallel callbacks. You couldn't really mutate shared state. You couldn't import modules. You couldn't coordinate or cooperate with other parallel callbacks. Worse still, we couldn't detect if you were trying to do that, so we just crashed. It was just horrendous. More cons. Hackfest, don't even put this remotely into production. When it didn't crash really fast, but crashed a lot. Windows only. If you want to have an open source project be dead on arrival, make it Windows only. And it wasn't just like, like in a day I could like recompile it, get it working with Linux. It solely used like Windows APIs for which there are no counterparts to this day on Linux or Mac or anything like that. So yeah, had no chance of running in like a reasonable amount of time on any other platform. And then there was Python free threading. Best thing that's happened to Python since its inception. So I think it's, my understanding it was pioneered by Sam Gross, an engineer at Meta. Python 3.13T is the first released kind of almost a bit over a year ago to have this new free threaded mode. So it's here, it's like finally here. We can run code like this. I guess you can kind of, you can run code like this, and it actually leverages multiple cores simultaneously. So that's a little simple example. A more involved example. So from thread pool executor, you can basically spin up these walls and then wait on them and do all that kind of stuff. It's not quite the panacea. There's, the third-party. I mean, it's getting a lot better. When I wrote the article at the start of this year, it was pretty brutal. I had to compile TikTokin by myself and Rust, and it was kind of a mess. It's progressively getting better. It is still kind of quirky to install it. You have to do this weird, at least with Conda, you have to do this weird little Python-free threading thing. These will all eventually go away. The plan is for it eventually to be the default, but this is kind of decades worth of time and engineering work. It does have the full support of the Python Software Foundation, Steering Council, and industry. So, a lot of these massive companies like the Microsofts, the Metas, the Nvidias, we're putting, we can see that this is the long-term future for Python. And you can still do really cool stuff with it today, which I can hopefully demonstrate shortly. So, crash course. All right, the whole topic of this thing was to do PyTorch inference. So the article, I really didn't have any exposure coming into PyTorch, both from a PyTorch perspective nor LLMs. Andrew Karpathy, for those that are aware, he has this YouTube series on deep neural networks. He's professor at Stanford and has a long and distinguished LLM history and just general dominance or prominence rather in the AI field. He's got it's literally 20 hours of content across 10 videos. And I guess I was fortunate enough to be able to actually watch it all. It took me about 2 weeks, so it probably took between 40 and 50 hours to really appreciate it. But it basically takes you from first principles of the tokenization to the backprop to everything to actually building and training your own GPT-2. So phenomenal series. If you want to actually know more and understand how LLMs work, highly recommend taking a gander at this playlist. Super useful. So equipped with the final video in Andre's series is called Let's Reproduce GPT-2. And he has a GitHub repo with accompanying source. So I was able to train a local GPT model from scratch. Took 3.5 days on a really old workstation I got from an old employer. And then I ran it on a 5090 and it was a lot short. I would have saved on my electricity bill at least that month had I done it on the middle 50. But it basically, it outputs this thing, this model underscore 19072. The 19,000 thing is the how many steps it was trained for. Quick little sidebar. So this is the attention is all you need paper. The reason I'm bringing this up on the screen is because you can kind of see the queues, the queries, the keys, the values, the general architecture that was presented in this paper still persists to this day it's the foundational thing that all LLMs are built on. So the source code for this is going to be really quickly, but the source code, again, this is all available. But the idea being that you have one of these causal self-attention models, you've got your multi-layer perceptron, some blocks, and then the actual, the GPT module itself. And then the inference is done via one of these generate motions. And again, skipping through this really quickly because we've got a lot to cover. But this is basically it. This is how you do inference and how you do text generation. So it was quite fascinating to see taking a model from nothing up into the actual generative nature of how these things work. So in a simplified Python session, you would load it from a local pre-trained thing and slap it onto the GPU. And then you can kind of see the structure. So you can kind of see some of the correlation between the features that we had, the layer norms kind of match that diagram. But this is basically that diagram that I depicted is pretty much evident in this model. So the real thing, how do we actually generate text? So this is my standard prompt that I use, model.generate. It's as simple as that. Maybe present a seed, and you get back something like this. It's nonsense. So this was trained on EDU FineWeb 10b. I don't know, what is that? I didn't look at it. But it knew enough, or it's captured enough information for it to at least write sentences that resemble English and kind of are topically relevant to Albert Einstein. So it was kind of funny. I did this and I'm like, that's interesting. What would happen if I trained the model for 2 phases and then did a generation on that. So I did that as part of an ablation test, and it just generates absolute junk. And it had an F-bomb in there, which I had to censor out for some reason. But it's just hilarious that it goes from generating absolute nonsense to coherent sentences, and then obviously actual seeming intelligence once you get into the billion parameter count. So the road to parallel PyTorch inference. to recap, so we've got Python free threading, we've got this janky GPT-2 PyTorch model that generate text when prompted. So the next question being, and again, this is putting myself in my shoes at the start of this year when I was writing this article, does it work when called from multiple threads? Like, what happens when we call model.generate from multiple Python free-threaded threads? So obviously, the simplest way to answer that question would have been just like try calling it from multiple threads. And what I find the most amusing about this is I was in Vim writing this slide, and I had Copilot enabled, and it literally just like, in less than a second, showed me the code that I probably could have just run to actually test all of this. Yeah, so that's all it would have taken to test that. So did I do that? I did not do that. I did not call it from multiple threads. Instead, I mean, because, why do something in 30 seconds when you can spend 30 hours on it? A quick test, that would have been kind of boring to see if you do it from multiple threads. So what would have been really cool if we could write a multi-threaded async IO HTTP server and expose a generate style get endpoint for doing inference and have it stream tokens in real time. That'd be kind of cool. Because like, when have you ever interacted with an LLM and it's like you ask something and then you wait 3.5 minutes, and then you get the whole thing back. You generally, all of the interfaces have a streaming type interface, where as soon as it starts generating tokens, it's fed straight back to you. So obviously, I wanted to like mimic that. And then, wouldn't it be great if we could implement it using all of the new async IO Python libraries, so like the async generates and the async function definitions. And then, just to top it all off, let's try and vibe code a fancy React front-end web UI for it all. So that was kind of what calling model generate from multiple threads is boring, and building this elaborate thing, far more fun. So there is software that exists. This is the Parallelopedia. It's got a Python component and a Node React component. I don't know any JavaScript. I don't think I've looked at the code at all. I wasn't joking when I said vibe coded. It was very much a interactive cursor sessions taking care of all that. And I don't really want to know JavaScript. I have no interest in learning that. So LLMs allow you to be ignorant of other programming languages you don't care about. Win. But yeah, you would basically launch a server, provide a couple of app classes, and again, I'll provide links to this for folks that are more interested. Demo or video if demo isn't working. So this is, I think I wired it. Oops, this is wired, so I can pause this. All right, so this is my little React UI. So you've got your little prompt here, and you hit submit. When I captured this, I forgot that I'd implemented round robining between the CPU and GPUs. So is this playing? Okay, so submit. So this seems fast, but I was like, well, it's not as fast as I remember. So it's got like a little show header. In this show header thing, you can see that the model device was CPU. So there, again, vibe coded some advanced options. We can go in and you can select it. So all right, let's make it run on the GPU, and then like try that again. And then obviously way faster, like orders of magnitude faster. I think I try that again. Yeah, look at that, 8,000. And then whack in a much longer length. It's still generating like plausible, and then depending on like what seed and max length you use. But you can also see the prompt speed degrade because it doesn't do any like key value caching or anything like that. But I actually have, so that was the live one. So this exists, it does exist today. Let's see if, look at that, it's live. Granted, like I'm not actually demonstrating free threading here. I'm demonstrating something like single threading accessing thing. We'll get into that in a little bit. How it works. So there's an async IO-based PyTorch model generation routine that yields a single decoded token at a time, which is it's different to how the generate things normally work. Leverage HTTP chunked encoding. So if you ever want to like stream something like this, chunked encoding is a great way to like bang that out really quickly and have it functional. The client doesn't see any of the chunks. By the time the client sees it, it reassembles and gives you that streaming effect. So to give an example of that, like I'm just curling the generate endpoint here, and you would get curl would just reassemble the whole thing. But if you pipe it to a manual HTTP GET request and then pipe it to netcat, you actually can see the headers, and you can see that, okay, we've got our transfer encoding chunked. We've got it sends the prompt straight back, and the way that it works is you have the length prefix and then the length of the next chunk that you're sending. So 3, the length, and a lot of these start with spaces, as you can say. So the length of space is 3, and that's really all there is to it for the sliding. So does it actually work in parallel? So I captured a couple of screenshots. It does. It absolutely does. The next side is an elaborate TMUX synchronized pane session where I had like 6 boxes at home that all hit this endpoint, and you can kind of see it. This is a GIF, so I can't really pause this, but you can definitely see that it at least plausibly looks like it's. I'm going to do a little zoom here, like they're all kind of running at the same time, and then it should restart. I never used this zoom it thing before, so there we go. Look at that. And you can see like they're using different seeds, so obviously the generated text is different as well. All right, so definitely works in parallel. The next one is, I don't know if anyone's used BTOP. So BTOP is this funky, like improved version of HTOP. But this is the old DGX machine. So oh my gosh, oh boy. Load test, let's try that again. So in the foreground, we've got like a little HTTP load testing thing on a completely different machine. It's 14 threads, all just doing simultaneously hammering of that get endpoint. And you can kind of see on the GPUs in the background here that they're all, it's round robining between them. It's leveraging all of those. You're getting like multiple cores are getting used up here. So yeah, I mean, it basically works. It's like you just can't do that without free threading. Oh yeah, let's get out of this zoom mode. Right, so, went a little too far there. Right, so some charts. So again, like as you would expect, the performance is a lot better. There's no, you're not losing anything here. So on the left, we've got a latency distribution with haven't learned my lesson, I'm gonna keep zooming. So you've got the latency on the, wow. Maybe I should stop zooming, on the left-hand side. And then obviously like flatter is better, the more left the line is, the better. The worst latency, like the tail end, was like still about 350 with the GIL turned off, like so free threaded mode. Whereas with the GIL enabled, it's obviously a lot worse on it's like 1.75 seconds. Requests per second, 70 versus like 7.35. So again, bigger is better. What's the catch? So with regards to Torch and performance, Torch Dynamo is this cool technology that they built in PyTorch 2.0. You whack a decorator on your method, and it does a whole bunch of cool stuff in the background and compiles it and makes it run much faster, presuming there's nothing that causes what's called a graph break, which is basically like, can it work out how to like basically compile like all this stuff to do an optimal GPU representation? So unfortunately, it doesn't work with free threading, just not even close. Doesn't work with async def generate machine routines either. So yeah, you're not going to be getting like max performance from your GPUs by doing like what I've just shown here. But also, I just whipped this up in like a week. So like, how could you get max, especially on the latest GPUs, it's tough to get max performance out of them without a lot more work. So there's no batching, there's no KV cache, there's no paging, there's nothing like that. Much better tools for the job if you're actually like trying to deploy a production ChatGPT style server. So NVIDIA Triton, VLM, they're all built to deal with this sort of stuff in a much more efficient way. That being said, this is still pretty cool. Like you still have, you can do model inference in a multi-threaded Python context. So even if we're not max performing, it is still pretty cool that we can do model inference. So granted, that model, maybe useless is one word I would think for it, but it also at least demonstrates the technology. And you can think of a lot of different apps that would have that would benefit from being able in their workflow to farm out to do some inference on some incoming set of data and then continue on with what it was working. So infinitely better than multiprocessing though. There's no expensive context switches. There's no GPU context switches. There's no memory waste due to the duplicating of all the models in multiple processes. And with an asterisk, it also works with contemporary models from Hugging Face. So if you look on here, so actually, and again, all vibe coded, and this, you can kind of select a little model here. I tried this at home on a machine that had a better GPU than this 12 gig one here, and it worked. I tried this before I left, and it kind of killed the GPU. So these models aren't really designed for running on a laptop in parallel in a presentation. So I'm not going to demonstrate the LLM one, but it does work. And I did mention Hugging Face in the abstract, so I thought I should mention that now. But so, in the real world where Python just gets stuff done, so for every production one of these like public-facing ones, think of the hundreds of thousands of internal apps where teams, leverage Python to get their work done. So one of the really common patterns that I observed back in the consultancy days was, you would load it, Python process, you would load a bunch of reference data, could be account, customer details, stock details, geographic data, entity data, generally called dimensions in data warehousing parlance. So concretely, that could be like NumPy arrays, arrow files, data frames, whatever. And then you would process a bunch of things that refer to that reference data. So it might be transactional data or, whatever. But it's very much a process of like loading these batch processing things and doing per, item transaction processing, with each transaction referring to things that are fixed, these dimensions. So, bank transfers, ad clicks, stock ticker data, and these are fact tables in the data warehousing parlance. And then this would be brutal in the multi-processing days, because every single one of your, if you had a multi-processing based approach, every single one of these processes would have the duplicate overhead of having to load all this static read-only reference data. Huge startup costs because everything's loading everything serially. So this is like literally the thing that Python free threading is excels at. So, well, that was weird. That was a weird jump. Spoilers. Generating text. Can you tell I didn't rehearse this? Demo we got there. What's the catch? Okay, yeah, cool, next section. All right, so segue, putting the Opedia in Parallelopedia with an embedded Wikipedia. To hammer home the point that Python free threading really is this good. So especially when it comes to loading large data structures in parallel, and then being able to reference them via multiple threads running simultaneously across multiple cores. So let's just, this is my line of thinking here, let's just straight up host Wikipedia in the same process. Specifically, we want to not just host it, what does that even mean? So we want to provide a couple of endpoints. One is provide a means to prefix search every single Wikipedia title. So any given article that you go to on Wikipedia, that's what I'm referring to when I say a title. So by prefix search, I mean like if you start typing in Dave, like I want to see all the articles about Dave, and then provide a means once you've selected an article to actually look up the content associated with that article. So on embedding Wikipedia, to do what I just described, it's actually all that's needed is two simple data structures and memory mapping. So the prefix searching, I use a try that of all titles mapped to the byte offset of that title within. So Wikipedia allows you to basically just download an XML dump of the entirety of Wikipedia. So it's just an XML dump that you can get the byte offsets with like a simple egrep expression. And then the tree facilitates this prefix matching. And then for the article lookup, if you have a sorted array well, I use a NumPy array, but it's basically just a sorted array of like 64-bit byte offsets of each title within the XML dump. Because the tree is like a key value store, once you've identified the title, it will have as its value the offset. So once you know the offset, you can figure out what the offset of the next, or the end offset, by just doing like a binary search and figuring out what the next offset that comes after you is. Yeah, more detail. So I actually upload all this. So it is like theoretically possible to actually duplicate all of this in not on my machine context. So this is it. This is Parallelopedia. It's got like a little wiki, obviously React to Vibe JS, but you can basically like type stuff and it will do a prefix search, and then you can click on any of these. So I'm going to click on NVIDIA CUDA compiler. The media wiki format kind of useless, so I was like, well, that looks terrible for a demo. Why don't I try and farm it out to Pandoc? And Pandoc magically will convert media wiki format into a beautiful HTML format one, presuming it can pass it. I picked a couple. I think if I typed in CUDA, it doesn't work on CUDA because there's some weird encoding in the XML dump. But just to prove that that actually exists. So this is on what's a WSL2 instance, so it's got 32 gig of RAM associated with it. But I can type in Dave. Let's type in, oops. And as long as I type in 3 characters or more, it will go and do a prefix search. So there's 4,492 articles, and they've all just been returned to me. So that was from the prefix search. So let's click on Dave Amadillo. No idea who that is. Let's Pandoc it. So apparently it's a professional hockey player. So all of Wikipedia in a single hosted Python process. It's also doing like parallel PyTorch inference and stuff. So here's some sort of specific things that if you did want to, or some tips on getting the most out of free threading. It's not one tree, it's 83 trees, and the ordering here is the first number before the underscore is the ordinal value of the first character of the title, and then the next number is just the number of things the number of titles that are in that tree. So it's not distributed well, but it's much more efficient with prefix search trees to partition them like that. It's much faster to create them and much faster to load them in parallel. So there's only one sorted offset, just one big 120 meg sorted offset. And we can load them all in parallel. Like parallel loading is like 2 seconds instead of 12. Again, like I said, much quicker to create them like that. The lookup of the tree is like OL, where L is the length of the title, and then the binary offset lookup is a log n inset. And then you can find from the article, the offsets, you can figure out literally just the start n byte will give you that article within the XML dump. So with 2 data structures and an mmut, you can host and index in a somewhat useful way the entirety of Wikipedia in your same Python process. It's also doing other stuff. Cool. So so the way that it works, there's an endpoint for the offsets. So that, when I first typed in that thing and it gave us the 4,000 daves, what it would have done is it would have given this this set of byte offsets and titles here, and then you can do a byte range lookup. So then the React client would have issued, having just been told, if you ask me ask for me at this article, this byte offset start and end, then I'm going to give you those bytes back. And then to get the actual the title with the pandoc, you can just send it to this wiki/name. So yeah, the summary, so the prefix searching is done by the offsets. You get all of the title, start, byte, offset, and end offset, and then you can just use that start and end to request the one you want. Alternatively, if you know the exact title, you can actually just look it up directly. So the tries, or the trees, depending on how you want to pronounce them. So it's only 1.2 gig on disk. It's roughly about 6 gig increase in the RSS of memory once loaded. This would have been brutal in the multiprocessing days, assuming that this was your only expensive data structure. So you've got 64 separate processors, each consuming 8 gig of RAM. You would need at least half a terabyte of RAM just for the RSS of processors, assuming they're not doing anything else. So realistically, you're going to want at least nearly 2 terabytes, a terabyte of RAM in the machine. And it just gets worse as time goes on. The Blackwell machines that we have are 224 cores. And they, you'd need 1.7 terabytes of memory. Granted, they ship with 2 terabytes, but that's not really the point. Okay, so my little point about Hugging Face was that you can, it works. So it was kind of cool. It was kind of cool to see that I picked the Llama 2 model. The first one that I captured didn't have anything of, it didn't really do a cool thing, but you resubmit it and you'll get a new one. So it's actually possible. I mean, the reason I put this in, there's no one's deploying GPT-2 to do anything, but you can get a lot of use out of contemporary models, presuming you've got sufficient GPU memory and stuff like that. And man, don't tell me. And the most abrupt segue ever. Questions? All right. Wow. I'm going to put this up. So let me talk a little bit about this, and then I'll take some questions. So this deck, this is always accessible from this. I'm actually on that website now. It's in the Trent.me up the top there. So this is if you want to go back and look at things in more detail. And then if you want to work out how the deck was actually put together, there's the source of it is here as well. The original PyTorch free threading article is over here. That has a huge amount of more detail on pretty much every aspect of what I've just described, so I didn't want to go into too much detail there. The Parallelopedia is where all the Python glue lives, that you can see how all of this stuff is put together. And then if you actually wanted to download the data and try this for yourself, then there's some Hugging Face links as well. And contact, if you need to contact me and complain that nothing actually worked when you tried it at home, feel free to hit me up on any of those avenues there. And then, man, kind of on time. All right. Any questions? Any thoughts? Any applause? Everyone's like, why, thank you. Thank you to Hannah for being so patient. Wow. We're going to a toy store after this, so that's what she's more excited about. All right. There's no... Yeah?
Thank you. So questions?
Hey, so I wanted to ask, I recently graduated. I'm trying to get into machine learning and deep learning more. And I think there's sort of like two paths there. One of them is applied. So that's understanding the math and how to actually use these models for real data. The part that I understand less is definitely systems, and that's definitely what you're stronger in. So I wanted to get your opinion on maybe where I could start. What are some good resources?
Good question. How would you encapsulate the systems part of it? It's ironic. Like from my perspective, I'm like even when I did the LLM like crash course. When I said I understood the math, it was very heavily like air quoted, and I've since forgotten how it all works. So great use of time that was. How would you specialize? So I think from my perspective, at least sort of like career trajectory, always interested in operating systems. So, and again, the reason I ended up at CrowdStrike, it was either Microsoft kernel team or CrowdStrike, but I wanted to work in the kernel. So I think working on kernel-based, either whether it's Linux or Windows, gives you a huge appreciation for how everything actually works at the fundamental OS level. And I found especially in hiring people and in general experience, the folks with like understanding, what's the difference between, so I could list a bunch of things that are wrong with, or a bunch of potential pitfalls that would go wrong with having an mmap-based approach here. So mmap against NFS is really slow. Mmap is like a page at a time. So if you're seeking around, there's no prefetching. So you need to like do some prefetching. But all of that knowledge comes from a pretty concrete understanding of the OS fundamentals. Likewise for the hardware, like I used to love, I still think I would enjoy assembly programming, but I spent quite a bit of time ensuring that I could actually still keep writing stuff in assembly from scratch, and that's a humbling experience, if anything. Very tough to do on the GPU side. No one's writing like raw. Well, some people are writing raw PTX, but if you're at the ability where you could at least understand assembly, so debugging C code and that kind of stuff, that has a huge benefit. So yeah, the lower that you can understand, everything else kind of fits in on top of that. In terms of system design and stuff, I don't have a good answer for that. I don't know. Yeah. Hope that helps. Anyone else?
Any more questions?
You packing up for me, Hannah? Thanks.
So Python now has at least 2 ways to do concurrent stuff. You talked about free threading. There's also sub-interpreters.
Yeah. I was wondering if I was going to ask about,
and I wonder what, as people are starting to implement on top of this, there's got to be some sort of guidance on when do you go sub-interpreters versus threading?
Here's my take. Never use sub-interpreters. So free threading has a small performance hit. It's not that bad. It's in terms of what you're getting, the cost benefit is huge. Sub-interpreters, the isolation, the thing that I really want to leverage is being able to have all these parallel threads access these massive data structures in, I don't want to have to do IPC boundary stuff and sub-interpret stuff. I want all of them to share the same Python objects that persist. So I don't even know how the sub-interpreters work. That's how little I care about them. So personally, free threading. And surprisingly, the only time free threading crashed for me was this week, and I've been banging on it for about a year, and it was some random Python media wiki from hell, the literal name of the package is media wiki from hell, and it had it just wasn't up to date with, I don't know, it was crashing in some weird and wonderful way, but obviously it wasn't. It's a very old package, so. But other than that, I'm kind of surprised. PyParallel crashed all the time. You did anything, you sneezed and it would crash. So I think they've done a phenomenal, the folks at Meta have done a phenomenal job productizing the free threading. So sorry for those that work on sub-interpreters or anything like that. Just ragging on your work. Oh, really? Wait, this uses NumPy in free threading. Oh. Depending on what you're doing, yeah. So when I had to hack NumPy to work with PyParallel, the first thing I had to do is basically put a TLS cache around a lot of the stuff. So a lot of these programs that were written in a single-threaded world were, they would do a lot of caching in globals with the interpretation that like no other thread's going to be racing for that, and that all breaks in free-threaded land. So.
Yeah, I guess the follow-up question to that is, how worried should one be to just throw your workload?
Just YOLO it?
Yeah. Google has...
Well, it was interesting to see no one put their hand up that they're actually using it now. So, yeah, good question. I mean, I would absolutely be... even if it was like much longer days and regularly running into crashes, like the payoff is absolutely there for free threading. Right. So it really depends on, like I would do it, but I'm super biased. So yeah, I would love to have a problem where I'm like, oh, I would love to throw free threading this.
There is Google has the sanitizer images for Python, so that at least tells you when things are crashing.
Yeah.
As opposed to you just crashing.
Just find out.
So, but it's it's not production ready because you won't be able to do that.
Yeah, it's tough. That was the thing that I'm like, man, from the experience from PyParallel, it's like, wow, it's going to be like, who's going to attach a debugger to these things in live every time they crash? Like, that's not a good user experience. And then, like, man, imagine the amount of like engineering tools you would need to build in order to sufficiently support, multi-threaded debugging and all that kind of stuff. So it'll happen in time. There's no way that they're going back on, this will be the way forward. So, and thank gosh, because Python it's literally the best thing to have happened to the language since inception. So that's my hot take. Again, very biased. All right.
Maybe one more very quick question.
Yeah. It's my boss's boss's boss. Sorry if I released some like confidential Blackwell information there. I'm pretty sure it wasn't confidential.
Yeah, I'm just curious. Cooperative thread, like threading, actual thread, like what you've done here is like pretty cool. You're sharing some state, going back. But say I want an actual parallel algorithm, like I'm doing like some parallel merge sort or some something like that, where it's actually I want cooperation between threads. How does free threading?
A lot tougher, and the reason I didn't do anything like that was specifically because it is a lot tougher. So I was able to bang this out in, basically I took all my PyParallel code from way back and then just kind of made it a bit nicer and more modern and ported the async IO stuff. But actually doing like parallel cooperative stuff, much harder. So, I mean, Python offers threading and locks, so you would need to introduce, you would basically need to mirror, like just say you were writing it in C++, you would need to mirror the locking primitives and the synchronization primitives, which Python has, and they work now. You can have like read, write locks and all that kind of thing, but it's a lot more work, and you would undoubtedly run into a lot more sort of crashes and issues.
But you don't have it at the Python layer yet, right? Like right now, like all the locks are at the CPython layer and the...
No, the locks are at the Python... Yeah, no, the locks are at the Python layer in the way that I think you're asking. So you would be able to write like a mutex locking, and it would work the way that you would expect with Python bytecode.
Okay.
So...
But I can't get out of the GC... Like, what is it? Immortalization?
Yeah.
Object immortalization isn't at the Python layer?
I don't know how you would... Yeah, I don't know how you would do that. So that's... Basically, they reserved a little bit in the ref count bit where if that bit was set, the object would never be garbage. Like, great idea. I think it was it's basically what you did in PyParallel. Just don't reference count. Like, you'll be fine. So I don't know how you control that from Python though. And there's certainly use cases where you could. That weirdly, some things are faster because there's only one generation of GC now in free threaded, and typically things perform better in these async IO ones where you're doing the callbacks that you're running in these multiple threads. Almost all of the allocations or object allocations that are being done are very quick and short-lived. Like they stop persisting at the end of the callback. If you've got things, parallel forking out and joining back in, that's a lot more complex, and then you're paying a lot more cross-reference. When a Python thread is inc-refing an object that it didn't create, that's a little slower. So there's all kind of little caveats there that I just avoided by not doing any of that. Okay. So, I mean, I had a week-ish, so get done what you can. All right. Thanks, folks.
So let's thank Trent again.
Thank you. Thank you to Hannah as well. Thanks for being so patient. Cleaned up, look at this. Oh, I love it. She's like, toy store now. All right, thanks, folks.